Hey everyone, my name is Damian Brenner. I'm one of the project leads at Zeppelin, and here we are live with Federico Bond. Hi Federico.
Hello.
So Federico is the founder of one of the most interesting startups in the blockchain space called Signatura. They do digital signatures and notarization on the blockchain. He's a fellow Argentinian and friend of ours and member of the Zeppelin community. So Zeppelin, it's an open source framework to build secure smart contracts. And we have a community that many of our members, they will begin this year, 2017, to give talks about smart contract development and security. So Federico is our first guest talking about Solidity and Ethereum Bytecode, understanding the compiler internals. So the idea is for Federico will explain how compilers work in general, while diving into the Solidity compiler code to see how it solves each task. The talk is going to be quite technical, but there's no need for everyone to understand how compilers work beforehand. If you guys want to do any questions, we have a chat on the side, so you can write some questions on the chat. We'll be answering them, and also we can have some time for questions in the end. Okay, Federico, I'll let you take it from here.
Okay, great. Let me see. I'm going to share my screen. Right here. Okay. So this talk is, as Demi said, about compiling Solidity to the Ethereum bytecode. So if you know a little bit about how Ethereum works, what it does is it creates an abstraction of an actual machine, which is called a virtual machine. This virtual machine executes instructions in a way that guarantees that every transaction will execute the same way in every node in the Ethereum network. So contracts in Ethereum are written in a couple of different languages. One of the most popular of them is Solidity. And we're going to see how Solidity works and how the code can how can we compile source code in Solidity to this bytecode that the Ethereum virtual machine runs. So as Damian said, I'm the CTO at Signatura. We do digital signatures. I have been developing software for the past 6 years and doing Bitcoin development for the past 2. And I never programmed a single line of C++ until a couple of weeks ago. In fact, I very much dislike that language. And I hope that I would never have to learn it. But you know how this ends. Solidity is written in C++. And I really like it to learn how it works and see in what ways I could contribute to it. So I had to suck it up and learn C++. So this talk is a result of this journey of me trying to understand how the Solidity compiler works. I had a slight idea of how compilers worked in the real world, but I never had any experience with one before. So it was an interesting learning experience, and it taught me something very important, that is that it's really useful to just dive into the source code, as Obi-Wan Kenobi says, and really go through it, try to understand it, spend time into the source, go look into how a certain project is structured, and that can give you a very good idea about in what ways you can improve it and how all of that fits together. And it's usually something that you won't find in the documentation. So whenever you're in doubt, use the source, which is a very good resource. Okay, so conceptually, what's a compiler? A compiler is a program that transforms source code, like the one you see above, into some bytecode, some machine code that computers are able to understand and execute. That is a sequence of instructions encoded into numbers, into specific opcodes and data that runs inside this virtual machine or into a real machine. So how do we do this? In fact, compilers are one of the most complex pieces of software, but fortunately, we understand very well how to structure them in a way that makes them comprehensible and that allows us to deal with this complexity. So compilers are usually structured into different phases. We'll see all of this in a moment in the Solidity compiler. First, we have the parsing phase, where we take a stream of characters from different files and transform them into what we're going to call an abstract syntax tree. And I'm going to dive into that later. So that's a tree representation in memory of the file source and all its instructions. Once we have that tree, we're going to do some sort of syntax checking to make sure that everything is okay. Then we're going to do type checking, static analysis, and finally, we're going to meet code specific for our target computer. This is how most compilers work. Now, there may be some compilers that have more or less of these phases, but now this is very similar to what the Solidity compiler does. And so we will use this as a base to understand how all of this works. So parsing. Parsing is about transforming the source code into an abstract syntax tree. So this is actually structured into several steps. We might think of it conceptually as going from the stream of characters in each of the source code files to the abstract syntax tree, but in reality, it turns out that it's easier to split it into two steps. So this is what we want as an end result. This is an abstract representation of the syntax that is written in a file. So for this very, very, very simple example, where we assign the sum of 1 plus 3 to a variable a, we can see it as the tree with a couple of literals with values 1 and 3 participating as left and right operands in a binary operation. And all that expression is assigned to the identifier a. So when we move from the stream of characters to the abstract syntax tree, we forget about white space, about semicolons, about comments and all that, and just deal with what the meaning of the expression is. We also do some desugaring if there is some, if the source language has this kinds of sugar, syntax sugar, and work with an abstract representation of the syntax. So first step in building this tree is what is called the lexer or the scanner. So this is going to take the file characters and turn it into a stream of discrete tokens. So it turns out that it's easier to build our tree dealing with tokens than with individual characters. So you don't have to check at any when you go from one token to another, you can skip all white space, you can skip all comments, and just deal with the semantic structure of the different construct on the language. So we take this stream of characters and we output a stream of tokens. For example, for a simple contract, this stream of tokens could be contract, identifier test, an opening bracket, uint, an identifier paid equals 0, end of statement, that's a semicolon, and then a function with a left parenthesis, right parenthesis. This function takes no arguments, for example, and so on. So the Solidity lexer is actually taken from the V8 code that runs Chrome and Node.js. So if there were any doubts about what's the inspiration for the Solidity syntax, it's obviously derived from JavaScript. So they took the lexer and replaced everything else. Okay, so once we have a stream of tokens, we are going to build this parser. And there are different kinds of parsers, but most of those in production use some variant of what is called a recursive descent parser. So a recursive descent parser conceptually is built out of a set of rules. So a rule could be, like the example here, the rule for contract is the token contract, then an identifier, then an open, this is a curly bracket. Yeah, an open curly bracket, then the contract body, which is going to be another rule, but we don't care about it right now, and then a closing bracket. So that's a rule in this parser, but what we are actually going to see in the code is it's represented as something like this. So to parse a contract is to consume a contract token, then to consume the identifier and assign it to the name, consume the open bracket, then go recursively into the child rule for contract body, and then consume the closing bracket. After that, we return a node for the AST with the name and the body of the contract. Now, this consume function I just invented here is going to advance to the next token and check if it is equal to its argument. And if it's not, it's going to raise some sort of parse error. So in this way, we can map very nicely, and we can go from rule to the parser code. Now, of course, this is a very simple, very trivial example. And in many cases, we have to actually look at the next token to see which rule is going to apply. So we do some, what is called some peek into the next token to predict which path to take. But conceptually, this is very useful for understanding it. So before we move on, I will go to the Solidity code and see where all of this is represented. So if you want to follow along, you can go to the Solidity repo on GitHub, and you can press the. Once you're there on the source tree, you can press T, and you can find any file using fuzzy matching. So we're gonna go and look at the Solidity source code. So this is in libsolidity here. Hope let's make the font bigger. So libsolidity, we have a couple of directories here. We're gonna focus on the parsing directory here. And we find exactly what I mentioned earlier. We have a scanner, which is taken from the V8, has all these rules for dealing with characters. So we have checks, if it is a white space character, if it is a start of an identifier, or a part of an identifier. And all this is going to build tokens out of the character string. So for example, we have scan hex byte, we have scan Unicode. Let's see here, skip white space, scan a single line doc comment. These are all returning tokens. So we see here how we go from characters to tokens. Now this part is not very interesting. In fact, this is one of the most generic parts of compilers. They don't vary very much from each other. So we're going to do something more interesting, and we're going to go look at the actual parser. So that's in libsolidity parsing parser. Let's look at the header file first, parser.h. So we see here all the functions: parse pragma directive, parse import directive, parse contract definition, parse inheritance specifier. So there's a parse function for each one of these rules, which is what we talked earlier. So these are the parse methods for each one of the rules defining the grammar for a recursive descent parser. So let's look at the shape of this. So as a simple example, we can search for parse, parser, parse while statement, for example. So this parse statement does some look ahead. So it peeks into the next token and will choose, depending on what token it finds, which statement it belongs. So usually you only have to look at the first token to see which path to take, but sometimes you have to do a further look ahead. So this parse while statement does pretty much what you would expect. Instead of consume, this function is called expect. So it's going to expect a while token, then a left parenthesis, then an expression, then a right parenthesis, and then a statement body. And it's going to return a node for a while statement with this argument. So you see here, there's very little magic in this. Now there are some of these functions. Let me see. That are maybe a little more involved and a little more complicated than that, but conceptually they are very similar from one another. Okay, going back to the
Federico.
Yeah.
We have here a question from Jake from CoinFund. He says, curious, is this code written from scratch or generated using some kind of scanner parser generator?
That's a great question. The code is written from scratch. The argument for that is that it was easier for the development team to iterate on the language. I'm not sure I buy it completely, but that's the reason I found when I was reading through some of the discussions around this for writing it by hand. So yeah, it's written by hand. There is a documentation for the grammar in the Solidity official docs, but as it probably happens, it was very outdated with implementation as the language evolved. So I have been trying to move it closer to the implementation and trying to understand how it works so that other parsers and authors of code that works with Solidity can have an updated spec. Great. Any other question?
Not for now.
Okay, so we're moving back here. After the parsing is done, a couple of theories. We have an abstract syntax tree. It's very easy to define a new phase that works on the and does some stuff on the tree by writing a visitor. A visitor has a method for each kind of node that it can visit, and nodes can, from the top of the tree, can accept a visitor, and all the logic of going through each one of the node's children is handled by in a single place, and as a visitor, you're only notified when you walk through a node. So we will see how this works in practice in a couple of minutes. But this is a very useful abstraction for walking through the abstract. An accept method that can receive a visitor, and it's going to call visit with itself and its children recursively, so you can end up visiting the whole tree.
Federico, do you want to share your screen? Because I think there was a problem.
Okay, let me fix that.
And we have another question from Augusto Lembe.
Yeah.
Lemble, he says, Federico, will you show how the assembly code on the contracts is compiled?
Yes, I will be getting there towards the end of the talk.
Perfect.
Okay, great. We're back here. So you can see my screen, right?
Yeah, again, perfect.
Great. So we go from the visitor pattern to type checking. So what is type checking in this context? So to do type checking, you go through the tree and you assign types from the bottom upward. So we find here a literal for 1, for example, and we assign it a type of uint, for example. And we assign a type of uint to the other operand. So binary expression of a plus between a uint and a uint results in a uint. So the variable a must be able to hold, maybe not exactly a uint, but some type that handles that or can be cast to that. So we go through the tree trying to make sure that the types on the right-hand side of the expressions match the types of the left-hand side, or that they can be cast to one another. So that's what type checking does. Sometimes you have to annotate each variable with the declared type. So when you do like var a equals something, then you, at that moment, you assign a type to a, or if it's declared in the source code, if you do uint a, then a is declared as a uint. So that's type checking is visiting the whole tree and making sure that the types are right for every expression. Okay, before we take a look at bytecode generation, I'm going to show you how this type checking works very briefly. So types here, okay, let's see. Let's go, let's take a little bit step back to see how this works all together. So there is a file called compiler stack. Now, this is the core of the Solidity compiler. If we go here to this compiler stack.parse, for example, we see the phases very clear, where for each of the sources we have to parse. We parse them, then we, let me see. Then we run the syntax checker, and make sure there are no errors. Then we run some analyzers for doc strings. We resolve each names. And we perform imports. These are all of the phases of the compiler. And then we, this is resolving each name in the contract. Then we run the type checker here. If everything is right, we run the static analyzer, and we return the result of the parse. And down below, we're going to find the code for compiling, which is right here, which is going to take the source and actually compile each contract. So you see here the phases very clearly. We can go here to type checker, dive a little bit into how it works. So, for example, here, okay, this is one of the most complicated functions, but the type checker for contract definition. You see here that it's a visitor. So the type checker has a function for each of the nodes it's interested in. So here, it's visiting the contract definition, and it has all the functions here. So for example, it grabs the constructor for the contract node and makes sure that, for example, the constructor can be defined as constant, or that it must be public. So this is a type checker. It's a visitor, so you will find here functions for each one of the nodes it's interested in. And we're going to move to the final and most important part of the compiler, which is code generation. So,
Federico, we have another question from Augusto. He's asking what the static analyzer is going to do.
Okay, that's a good question, because I wrote the static analyzer. It's still very early, doesn't do much, but it checks, for example, that you don't use message.value on a function that is not payable. I think that's its main use right now, but it's done with the idea that you could do all other sorts of checks on the source code, and you have to do this, sorry, on the AST, and you have to do this after you do type checking, because you could, for example, that would be a very nasty thing to do, but you could define a variable called MSG that is different from the global MSG. Not sure that's allowed, but we have to do it post type checking, because if you only have a name, you don't really know what it points to. So if you use message.value in a function that is not payable, it's going to raise some warnings in the static analyzer. So that's very simple code. So we can check it right now, static analyzer. Sure. So it checks first that the contract, when it enters the contract definition, it checks that if it is a library, and when it resets the value when it ends the visit to the contract definition. And here we see that when we have a member access, that is when you do, for example, message dot something else, that's a member access of the member value, for example. We check here that if it is a non-payable public function and it's not a library, then we raise this message value used in a non-payable function. And so that's what the static analyzer does. So after we run through all these phases, we go to the codegen directory to find the compiler. And this is the code that is going to generate the bytecodes, we're going to take a look at how a simple while expression or while loop is compiled, and then we're going to see some of the things about how Solidity does function dispatch that will be very interesting for some people. So going back to the compiler, we have a couple of methods here. Let's see. Let's go to the contract compiler. Contract compiler. We have a visitor here too. Visitors are all over the code in any compiler. So for example, to compile a while statement, let's take a step back. I have a file here, I think a very simple while loop in a Solidity file. Let's see first the output of this and see if we can make sense of it. So if I run the compiler on this and output the ASM, we can see that here that to compile a while loop, we're going to first load this 15 constant. We're going to load A from storage, because it's a variable stored in storage. And this less than is a comparison operator. So if A is less than 15, and that is 0, that is, it's false. If it's false, then we're going to, if it's false, we're going to do this conditional jump. Jump I is the instruction for a conditional jump in the Ethereum virtual machine. So we push the tag that we want to jump into, and if the condition here is true, then we jump to tag 6. That is the end of the loop here at the end. If it is not 0, then we're going to do this A++ thing. You can see here the add bytecode and some loading of the A variable. So if this is all good, it's going to push the tag 5 and do an unconditional jump to tag 5. So what's tag 5? Tag 5 is this one here, which is the start of the loop. So we see here how when it reaches the end, it goes back to tag 5 unless the condition is false, in which case it's going to jump to tag 6, which is right after tag 5, the end of the loop. So you see here that there's very little magic on this. Some of these instructions depend on whether a variable is in storage or memory, but you can see there is some structure to this, and we'll see it in the code right here. So contract compiler. If we go to the while statement, there are some checks, and there is this creation of the loop start and loop end tags. Those are the tags that we saw in the ASM output. It's going to set up some continue and break tags so that continue and break expressions work. So first thing we do, we have this context here, which is storing all the bytecode. So we push the loop start tag to the context. We check if it is do while. If it's not a do while, the do while here is handled down below. We compile the expression, the condition. We check if the condition is 0. Here, we push the instruction is 0, and we append the conditional jump to the end if it is 0, that is, if it is false. And then we accept, that is, this is going to recurse into the while statement body. And we're going to append the jump to loop start. This is if the loop reaches the end, it's going to go back to the start. And we append the loop end. That is where we're going to jump if the conditional here matches true or false, actually. So you see that there is some sense to this madness that is compilers. So this is kind of this is mostly how this works. And we're going to see one last thing, that is how does Solidity do a function dispatch, which is not something that is very talked about. Maybe you have some ideas. The thing is, there is no notion of functions in the Ethereum virtual machine. The fact that your contract has different functions is an illusion created by the compiler. What is actually happening, and we're going to see this. Let's grab this test contract. This is the end of it. So let's compile Sol function. So I put 5 functions, so it's very easy to identify this in the output. So if I compile this to ASM, we're going to see, let's see here, this. We do a call data load. There is, we load the call data from the transaction, do some stuff with to make sure that we grab I think it's the first 4 bytes, but I could be wrong. It could be the last ones. So what we do here is we have, for example, push 4 of this constant. We check that if it's equal to the first 4 bytes of the call data, and we go to a certain tag conditionally. Then we push another value, we check if it's equal, and we push another tag. And we check another value that looks kind of random, and we check if it's equal, and we push another tag. So these tag 2, tag 3, tag 4, tag 5, tag 6 are every function start in the code. So what's actually happening here is that it's like a switch case where we switch on the first 4 bytes of the call data to go to a certain function. So this, if you have a contract with a lot of methods, this is going to take a linear time, I think, to check to which function does each transaction correspond. So be careful with that. I mean, this is not optimized. Or perhaps it is in the virtual machine, but from the way it looks, it is going to check into each function. So we're going to see how this works in the code. So we go to contract compiler. So if we visit a function definition, let's see, function definition. No, actually, it's in the contract definition. Here. Okay, so this is the code that does the function dispatch, compiling, append function selector. It's going to take a map of hashes to functions. This is a hash of 4 bytes, I think. And it's going to insert this. Let's see. It's hard to do it live. So what it's going to do here, going to get the, for example, here we have the checking of the call data size. If this is 0, then it's going to jump to the fallback function. So we see here how if you send a transaction with no call data, it's going to jump to the not found, which is I think the fallback function. And for each of the interface function, it's going to push the hash here and check if it's equal to the call data and do this conditional jump. So that's how function dispatch works in Solidity. And with that, pretty much out of material, I think. Okay, so conceptually, we can think of function dispatch as a switch where we hash the function signature, and we have code for going into each function. So that's all I have, and I hope you liked it and you understood more about how a compiler works and how the Solidity compiler works. And if you have any questions, you can send me an email or write me on Twitter. Thank you very much for being here, and thank you to Demi and Manu from the Open Zeppelin team for hosting this.
Yeah, thank you, Federico. It's been great, very interesting talk. We have many people here watching, and in case they have any questions, now they can write them, and we can answer them. Also, they can get in touch with you at your email and everything. They can get in touch with us. For those watching online and for those that didn't have the chance to watch it, we will be sharing recorded talk on our Slack. So zeppelin.org and join our Slack. Everything will be there. All the information will be there. So thank you, Federico, for being our guest and presenting this talk, and hope to see you soon. And thank you, everyone, for watching. Bye-bye.
Well, thank you. Goodbye.